Okay, hi everybody. So, yes, it is 3 a.m. right now, but when a 6-month-old baby wakes you up and you can't go to sleep, you might as well do some math. So, I promised to make a video explaining this one. Okay, so the point of this is to try to show that the gradient is 0. Now, the gradient at a point is a vector. And remember from chapter 1, exercise, if a dot x equals 0 for all vectors a, then we showed that x equals 0. Then x equals the 0 vector. So that's what we're going to do here, where x now is the gradient, and we have to show that something is 0 for all vectors a. Now, okay, so what are we doing here? We're on some open set U. Maybe it's here in the plane, and we have some function f. So f assigns numbers to every single point, and what we're finding here is that at this point, at some point p, f of p is a maximum. So f of p is a maximum, say right there. So the number that's hovering above this point is the biggest number. So this number is smaller, or the number hovering there is smaller, the number hovering there is smaller. And so what we do is if we move in any direction, A, then the number that's hovering in the direction A will be smaller than f of p. Okay? But that also holds if we move in the direction minus A. Okay? So the whole line in direction A would be P plus TA, right? And that's a line, it's one-dimensional, so we're going to go back to single variable calculus. So from single variable calculus, we know that that if a function has a maximum at some value, then the derivative is 0. Right? If there's a maximum, then the derivative is 0. That is from single variable calculus. If we had the graph of a function, right there is a maximum, and sure enough, the slope is 0. Okay, but f at p plus ta is now, if we're just restricting the values of f to this line, then we have a single variable function. It's a function, fcn is my abbreviation for function, of one variable. But we know that it has a maximum there, right? So no matter where we are on this line, well, as long as it's in the open set U, so for small values of t, it'll be in the open set U, and all the numbers hovering at these points are smaller than f of p. And so this function has a maximum at t equals 0. So this function of one variable with max at t equals 0. Okay, so let's apply, so then we know that the derivative is 0 there. So apply d dt gives, And now by the multivariable chain rule, we get the gradient of f times the derivative, the velocity of this curve, which is a. We get, so the derivative is 0, so that means that the derivative 0 is equal to the gradient of f at the point where t equals 0, which is, of course, then that becomes 0, and we just get p. Dot product c prime of t, that's the multivariable chain rule. But c of t is just a straight line, so the velocity is just that direction vector a. And that is true no matter which line we choose. No matter which direction vector a we choose, that line for any vector a. Thus, the only option is that this vector is the 0 vector. And we're done. Show that the gradient at a maximum is equal to the 0 vector. Okay. So that's all. It goes back to chapter 1. And also the general idea is that by restricting the function to values on a curve, we return to single variable calculus and can apply our results like maximums have the derivative being 0. It's amazing how often you can take a multivariable calculus situation and by choosing a curve, turn it into a single variable calculus situation. That's a good strategy.